Hello, my name is Bernie from Pre06 and today I'll be presenting on the topic of electrosurgical unit for my MEDDEV project. This is the table of content that I'll be presenting with. Firstly, the description of the electrosurgical unit. I'll discuss the background information and the application of the ESU. Secondly, the safety issue with the surgical unit. I will discuss the problems with the ESU and the possible solutions and recommendations. Thirdly, good practices to have when manufacturing, operating, and maintaining the electrosurgical unit. I'll discuss appropriate procedures that should be conformed to and the possible solutions, as well as the good practices checklist. Finally, I will conclude the presentation. Description of the electrosurgical unit. What is the electrosurgical unit? An electrosurgical unit is a medical device used in electrosurgery to cut, coagulate, dissect, fulgurate, and strain tissue. The electrosurgical unit uses high frequency 100 kHz to 5 MHz, also known as radio frequency, alternating current at various voltages 200 volts to 10 kV, which passes through the tissue to generate heat. An electrosurgical unit is made of a generator and a handpiece with electrodes. It's controlled using a switch on the handpiece or a foot switch. Electrosurgical units are usually used in eye surgery, gastroenterology, dermatology, and more. Electrosurgical units have two modes, monopolar and bipolar mode. The electrosurgical unit is made out of few components as shown in this image. Firstly, radio frequency oscillator. It creates the main high-frequency waves. These waves can be nullified in a range by embedding them, producing waves for cutting, coagulation, and merging. Secondly, function generator. Its function is to generate the specific modulation signal based on the selection of the wave shape. Thirdly, power amplifier. It works to amplify the resulting wave from the modulator and is controlled using the control unit and the switch. Fourth, modulator. To achieve more intensive coagulation of incisions, a higher peak voltage is necessary. However, to prevent excessive incisions and effects and carbonization, it is essential to decrease the mean power, and this reduction is accomplished by adjusting the alternating current, wherein the peak value fluctuates over time. One common modulation technique involves briefly interrupting the current flow at regular intervals. Typically, this modulation occurs so rapidly that users only perceive a change in tissue effect. The extent of modulation is indicated by the relationship between the peak value and average value of the voltage, known as the crest factor. Fifth, output circuit. This circuit adjusts the output voltage in the appropriate value to the active and neutral poles. 6. Power supply. It supplies constant voltage outputs in a range to each circuit's component specification. Next, electrode. Electrode plays a crucial role in either altering or maintaining physiological state of the body. When functioning as sensors, they utilize transmission signals to deliver electricity to tissues. In electrosurgical procedures, electrodes are usually used to either destroy or construct the dermis of the skin surface, whether it's superficial or epidermal, and are available in various sizes and shapes, tailored to the specific surgical task. An active electrode typically resembles a scalp blade, and current density varies depending on the size and the shape of the tip. There are three main types of electrode tips: needle tip, blade tip, and ball tip. All are made out of stainless steel. The size and the shape of electrodes depends on the manufacturer and the intended use. In electrosurgical units, electrodes are categorized into two types: active electrodes and return electrodes. The active electrode is a flat blade electrode. The purpose is for cutting and coagulation. The return electrode, it is present in the monopolar type. The return electrode provides the return path to the electrosurgical unit. 10. Hand tool. The surgical pencil has two modes, cutting and coagulation. A high frequency voltage and power are required for cutting. The power level varies from 100 to 750 watts, depending on the type of application. 11. Foot switch. Using a control circuit, the foot switch controls the radio frequency power output by turning on and off and controlling the flow of electricity. running to the electrode. 12. Cables. The purpose of cables is to link the various components together. 13. The grounding wire is the most important part of the generator as it prevents electric shock. 14 is the stainless steel for patients. There are two types of functions for the electrosurgical unit. They operate differently from each other: monopolar and bipolar electrosurgery. In monopolar surgery, the active electrode is positioned at the surgical site, while the return electrode, also referred as the dispositive pad, is positioned elsewhere on the patient's body. The surgical effect is produced by the high density current at the active electrode site. The circuit from the active electrode to the patient return electrode is completed when an electric current flows through the patient. The role of the patient return electrode is to safely extract current from the patient. Preferably, the current is dispersed into the patient and gather across the large surface of the return electrode to decrease the adverse heating on non-target tissue. If the heat generated over time is not properly dispersed, a return electrode burn may occur. An example for such usage is skin tag removal. In bipolar electrosurgery, the active and return electrode functions are both positioned at the surgical site, using the tips of the forceps. The forceps two tips serve as the active and the return electrodes, and on the only tissue grabs within the forceps is part of the electrical circuit. Hence, one tip of the forceps handles the return function. A separate patient return electrode is not required. Bipolar electrosurgery remains effective irrespective of the surrounding medium, allowing for coagulation in a fluid environment. This characteristic, known as wet field cautery, is particularly advantageous when attempting to coagulate in a moist environment. Bipolar electrosurgery is more often used to coagulate fine tissues, such as in neurosurgical and ophthalmic practices. Furthermore, electrosurgical units can produce a range of waveforms. The most common three are cut, blend, and coagulation. Pure cut waveform is a single nominal frequency pure sinusoidal signal in the radio frequency range, while blend waveform is a pure modulated sinusoidal waveform at 50 to 80% duty cycle, with a similar phantom frequency and a smaller modulation frequency around 25 kHz. The coagulation waveform is a small high voltage radio frequency waveform, followed by a long rest resulting in a low duty cycle in the range of 5 to 40% and a modulation frequency ranging from 20 to 50 kHz. Application of the electrosurgical unit. Cut, coagulate, dissect, fulgurate, ablate, and string tissues are methods used in eye surgery with the help of electrosurgical unit. Electrosurgery is applied in dermatology to cut, coagulate, or remove tissues. The most common applications are the removal of skin lesions, cauterization of blood vessels, and tissue destruction. Electrosurgery is also used in gastroenterology. The ability to cut and coagulate makes electrosurgery a preferred therapeutic equipment for gastrointestinal endoscopy. Safety issues with electrosurgical unit. My problem statement is how we can reduce the injuries caused by electrosurgical unit. Thus, we will be discovering the different type of preventive measures and precautions to have when using the electrosurgical unit. The first problem is interference. Electrosurgical units can produce significant electromagnetic interference. They can disrupt the functioning of other equipment, primarily due to the leakage of high-frequency currents. The leakage of high-frequency current in the ESU is due to 300 to 500 kHz output waveform utilized for their operation. This leakage occurs when the electromagnetic energy capacitively couples with specific metals present in the surgical environment. If the leakage surpasses a certain threshold, it can lead to interference with display or other electronic circuits within the operating rooms. The most significant risk arises from the unintended current flow to both patients and staff, particularly when unintended capacitive coupling of high-frequency current occurs with metal objects near the surgical site. The primary issue of the concern involves the pacemaker's inability to provide pacing energy once ESU is activated, necessitating the surgical extraction of the affected pacemaker. Furthermore, the passage of electrosurgical current through a pacemaker catheter has the potential to harm cardiac tissue at the electrode locations and could induce fibrillation. The solution to interference. Firstly, to minimize interference, we may reduce the silent period. We should to turn off the ESU off for a short period after regular usage. It will allow the ESU to rest and cool, decreasing the interference. Secondly, minimize the interference by using a low-pass filter. Thirdly, shielding of input circuitry. Fourth, an input electrode shaft will be with a brightly colored inner layer of insulation makes it easier to spot insulation failure, which may lead to leakage of currents. The second problem is burn. Skin burns are the most frequently reported and frequently happening at the written electrode site. Partial or complete detachment of the electrode pad from the patient is the most common issue. Patient burns can be a result of dense creases or bends in the surface of the written electrode. They can create local hotspots of high density current. Electrosurgical units are equipped with protective surface designed to minimize the risk of patient burns that may occur due to issues related to written electrodes. In the past, these units included a continuity monitor which prevented ESU activation in case of a break or disconnection in the written electrode cable from either ESU or the electrode. However, this type of monitor couldn't detect partial or complete detachment of the written electrode from the patient, potentially leading to patient's burns. Electrosurgical injuries also occur at sites other than written or active electrode. Burns to patients or operators can be caused by chipped, cracked, or damaged insulation on the electrode handles or cables. Capacitively charged leakage currents through electrode insulation and alternate current paths to the ground. The solutions to burns. The first recommendation is to avoid multiple usage of the ESU on the same patient simultaneously to decrease the risk of patient burns. Second recommendation is the proper preparation and vigilant checks of the written electrode site on the patient before electrode placement, and vigilant checks after the procedure. The written electrode site should also be checked periodically during the procedure whenever the patient is moved and when faulty operation of the ESU is suspected. Furthermore, some hospitals utilize specially electrosurgical electrode monitors during laparoscopy to decrease the chance of injury from the faulty electrode insulation from laparoscopic electrosurgical. The third problem is smoke. The thermal breakdown of tissue generates a smoke byproduct when ESU is used. Various reports have verified that the hazardous gas and vapors, bioaerosols, and both dead and alive cellular material and viruses are found in the smoke plum. When they're present at high concentration, this smoke may irritate the ocular and upper respiratory tract of the healthcare personnel and obscure surgeons. Additionally, the smoke emits a foul smell and contains mutagenic properties. The solution to smoke is to decrease the risk to both patients and staff. Hospitals should equip their operating room with a smoke evacuation system, limiting the smoke clumps before it could travel any further distance in the operating room. In addition, the surgeon should always wear suitable personal protective equipment. When smoke plum is emitted into the operating room, local exhaust ventilation is recommended. It has different types of designs and purposes, such as portable smoke, evacuators, and room suction system. None are without some hindrance to the ease of use by the surgeons. The irritancy of surgical smoke may disturb some staff harmfully despite the effective LEV. The fourth problem is direct application. Accidentally activating an electrosurgical unit is unfortunately quite common. Many of these units operated using pedals, which can be inevitably triggered by a surgical team member leaning on them or by placing a heavy surgical instrument on top. It is important to note that having one team member manipulate the electrosurgical instrument while another activates the unit carries significant tasks and could lead to adverse events. If someone unintentionally activates the ESU, they could potentially cause harm by applying the electrode to the wrong site or anatomical area of the patient, inadvertently shorting to another conductive material. The second most common type of electrosurgical injury occurs when the active electrode is energized accidentally while in contact with non-target tissue. Most of these injuries are due to inappropriate placement of the active electrode on the patient between users and activation of the unit by extending pressure on the hand switch or foot switch. ESU component failures. Issues when the active electrode, hand switch, or pencil and activation of other electrode. Solutions to direct application safety issues. The first recommendation when not using the active electrodes, it should be kept in the well-insulated safety holsters. It's essential, it's essential when the electrodes which have a layer of insulation to minimize the risk of direct coupling and are regularly checked in the sterile surfaces between users. The fifth problem is fires. Flash fires have occurred due to igniting flammable materials in an oxygen-enriched environment in the operating rooms after coming into contact with the ESU, resulting in fatal injuries to the patients. The solutions to fires. Surgical staff awareness, fire drill training, and identifying high-risk procedures can decrease the chances of fire. ESU should not be used in places with flammable liquids and materials or places high in oxygen. Good practices. Manufacturers should practice conformity to IEC 60601 Basic Safety and Essential Performance requirements of medical electrical devices. Good maintenance practices. Firstly, always refer to the manual. A user manual should be received from the manufacturer and be readily available in the practice setting. Instruction of use should be together with the ESU. Secondly, adopt consistent regular checks. If the manufacturer's service manual and inspection procedure are unavailable, it's necessary to establish the frequency of checks. Furthermore, many big electrosurgical device manufacturers suggest conducting semi-annual preventive maintenance tests to verify the unit performance. Thirdly, exercise a formal standard operating procedure (SOP). In the absence of the manufacturer's service manual and inspection method, the medical facility remains accountable for selecting and standardizing a testing approach. It's crucial to quantitatively assess the usability of the electrosurgery generator by comparing against the manufacturer's specifications. Or enhance your electrosurgical analyzer setup by incorporating additional test equipment for thorough testing. Many manufacturer performance inspection protocols necessitate electrical safety assessments such as ground wire resistance and chassis leakage tests. To ensure easy completion of the electrical safety component of the performance inspection, having an electrical safety analyzer readily available. Fourthly, enhance your electrosurgical analyzer setup by incorporating additional test equipment for thorough testing. Many manufacturer performance inspection protocols necessitate electrical safety assessments, such as ground wire resistance and chassis leakage tests. To ensure easy completion of the electrical safety component of the performance inspection, have an electrical safety analyzer readily available. Fifth, be cautious of test leads while testing. Minimize the length of all test leads and interconnecting leads, avoiding crossing or coiling measurement leads. Lengthy leads tends to function more like antennas rather than proper test leads, comprising accuracy. 6. Be vigilant with working with active electrodes. Avoid contact with the active electrode or return pad of the electrical surgical unit, or is activated in either cut or coagulation mode. Always switch off the ESU before adjusting or removing connections. Additionally, be vigilant of other flammable hazards in the vicinity. Conduct all necessary tests to ensure optimal performance. Power distribution test to evaluate the power output properties of the ESU. High frequency leakage current test. Measuring radio frequency leakage current is crucial as it can potentially cause accidental burns in patients. RECM test. The written electrode current monitor serves as an alarm system, preventing electrosurgery generator from energizing if the current flowing through the written electrode plate or pads exceeds a predetermined threshold. Inert gas flow and pressure parameters. Some electrosurgery generators offer the option to produce an inert gas envelope around the surgical site, effectively removing oxygen and reducing the risk of safety hazard. The test, the gas flow and pressure parameters for such inert gas outputs to ensure their Efficacy. 8. Utilize test automation for execution of test precise documentation of measurements and archiving data. Standardizing test procedures ensures all testing is registered, accurately, kept safely and neatly, and meet regulatory requirements. 9. Ensure electronic documentation and consistent archive of test results. Accurate recording of gathered data is crucial for monitoring and performance and safety of electrosurgery generated over time. Long-term analysis of this data facilitates predictive maintenance, enabling timely ordering and receipt of components for repairs. This approach saves costs and maximizes the availability of medical devices for use. The most suitable method for archiving test result information is through a database or computerized maintenance management system (CMMS). 10. The ESU cord should be always stress-free. The cord should lie flat and be free of kinks or knots. 11. Power settings should be confirmed between surgeon and operating personnel. The settings should be adjusted based on factors such as patient size, type of active electrode being used, the proximity of patient's return electrode to the operative site, and recommendations provided by the manufacturer. It is always advisable to always start with the power setting at the lowest level necessary to achieve the desired tissue effect. 12. The ESU foot pedal must always be covered with a plastic bag to prevent contamination during the surgery. Solution and recommendation. The ESU should have a solid-state generator operating within a frequency range of 300 to 1000 kHz. It should feature isolated monopolar and bipolar outputs and be equipped with hand or foot switches. For general operating room use, the maximum power output for monopolar cutting should be 300 watts and an open circuit voltage ranging between 200 and 1200 peak volts. Monopolar coagulation should have a maximum power output of 200 watts and an open circuit voltage of 120 peak volts for contact coagulation and between 1200 and 4600 peak volts for coagulation. Bipolar coagulation mode should operate at maximum of 100 watts and 200 peak volts. Bipolar coagulation mode should operate at maximum 100 watts and 200 peak volts. The unit should include a RECQM, independent output and visual audible activation indicators, following the AAMI and IEC 6060122 standard. It should also feature a power setting, display, and utilize a convection or fan cooling system. Actually, the unit must have an alarm capable of producing volumes higher than 45 decibels at 1 meter. Checklist. All accessories and metallic ornaments are removed from the patient before surgery. The handpiece should be placed in the appropriate holder when not in use. We should always refer to the user manual for instructions. Exercise caution when using active electrodes to ensure no flammable hazard is present. Perform rigorous checks on the ESU. Perform power distribution tests, high frequency current leakage tests, RECM tests. Inner gas flow and pressure parameters are at appropriate levels. Test automation. Test results are documented and stored appropriately. Power settings should adjusted to appropriate levels according to patient specifications. ESU should be sterilized and stored appropriately after use. In conclusion, the electrosurgical unit uses a range of radiofrequency waveforms to alter tissues. It has two modes, monopolar and bipolar mode. It has safety issues like interference, burn, smoke, direct application, and fire. The solutions are awareness trainings and regular check. Good maintenance practices are performing checks, tests, and appropriate procedures. Thank you for watching my presentation.